We're looking at a virus with a 35% fatality rate, more than 2,600 cases in 27 different countries. That is 10 times more lethal than COVID-19, and it is currently on the WHO priority list because there is no vaccine and no approved treatment. MERS-CoV isn't an hypothetical risk, it's a biological ticking time bomb. Current solutions are failing because they cannot match the speed or logistics of a MERS outbreak. Traditional antibodies are too bulky and dependent on cold chain storage, while small molecule antivirals struggle with low specificity and rapid viral resistance, with vaccine timelines still measured in years rather than days. The world lacks a true rapid response platform capable of neutralizing emerging coronaviruses strains before they escalate. Our project targets the exact key unlock mechanism the virus used to infect human cells. We have designed a 10 kilodalton miniprotein binder which doesn't just treat the symptoms, it acts as a physical plug that occupies the virus spike protein, making it impossible to bind the cell. What makes our approach truly innovative isn't just the AI design, it's the iterative solubility loop. Most AI proteins look great on a screen but turn into insoluble grease in the lab. We successfully stripped out the greasy residue to create a candidate having an extreme solubility with a gravity score of minus 1.52. We solved the developability gap that kills most biotech startups. On top of that, our protein is so small that it could directly be used for nasal delivery. The real value here is that we didn't just build a single molecule. We built a reusable biodefense framework. This pipeline can be redeployed against any other coronavirus variant within days. We're moving from reactive medicine to proactive platform-level biosecurity. We have the validated lead, the solubility data, and the speed. My colleague will now show you the rigorous pipeline that took us from a raw crystal structure to this optimized candidate.
So here's the full pipeline. 4 stages, each one feeding directly into the next. First, we ran arrow of diffusion to generate a protein backbone, then protein MPNN to design the actual sequence, then bolts2 to validate whether it actually binds, and finally peptiverse to check if it's as viable as a drug. What makes this pipeline novel is that we added a solubility screening loop between stages 2 and 3. Because our first round of sequences all looked good structurally but were predicted to aggregate in water, the screen is what led us to our final candidate. Firstly, we did RF diffusion. So the target is the receptor binding domain of the MERS-CoV spike protein, which is roughly 200 residues long and is used to latch onto human cells. We identified 8 hotspot residues on that binding patch and fed them into RF diffusion, which works by starting from pure random noise and iteratively denoising toward the protein shape that geometrically fits those hotspots. It generated 10 backbone designs, all with motif root mean squared deviation under 0.12 angstroms, meaning every design locked precisely onto the target geometry. We selected the 83 residue backbone as our lead. Then we ran protein MPNN to design the amino acid sequence to fit that backbone. Round 1 gave us 50 sequences, the top 5 went into bolts2 and showed strong predicted binding. But there was a problem. Every single one had a gravity score above 0, meaning they were predicted to be hydrophobic and aggregate in solution. The culprit was alanine, making up over 40% of each sequence. We ran a second round where we explicitly excluded alanine and sampled at a higher temperature to increase diversity. 27 out of 30 new sequences passed the solubility threshold, and our best candidate went from plus 0.4 to minus 1.52 on the gravity scale. Then we ran bolts2. We put all the 8 candidates through bolts2, which co-folds the binder and the target together and gives us an IP-SAE score, our interface binding confidence metric, where above 0.8 means very strong predicted binding. This is where the pipeline gets interesting, because the 2 soluble candidates from round 2 both scored below 0.35, meaning they gained solubility but completely lost binding, whereas our final binder was the exception. It scored 0.858, clearing the binding threshold, while retaining a gravy of minus 1.52. That combination is what made our lead. Finally, we use Peptibus to profile our binder as a potential therapeutic. Uh, it came back non-hemolytic, meaning it won't damage red blood cells, which is a critical safety flag for any drug candidate. The net charge of minus 1.5 at physiological pH and an isoelectric point of 5.76 both support stability and biological fluids. Finally, pulling it all together, our final binder is 83 amino acids with an IPSAE of 0.858, a PLDDT of 0.927, and a gravy score of minus 1.52. The bolster predicted complex also closely matches the original RF diffusion backbone with a TM score of 0.819, confirming the structure prediction is genuinely recovering the design geometry and not just hallucinating a plausible fold. Every metric we can compute computationally points in the same direction. Finally, for the applications and the visions of this project, the most immediate application is a nasal antiviral spray, delivering the binder directly to the respiratory epithelium where MERS-CoV enters. Because it's only 10 kilodaltons and very highly soluble, aerosol formulation is straightforward. More broadly, mini-proteins at this size can be freeze-dried into a stable powder, which means no refrigeration, directly addressing the cold chain problem in the regions where MERS actually circulates, in the Middle East. And perhaps most importantly, this entire pipeline ran in days. The same workflow can be pointed at any emerging coronavirus.